The question is, could you do an example on calculating deformation of a multi-segmented, statically determinate 1D rod? This is the problem I have chosen here. This is a problem that I have used in the discussions in one of the previous videos. Here we have more details to complete the problem definition. Basically, we have a 1D rod consisting of 3 segments fixed at point A. The rod is subjected to 3 external point loads at points B, C, and D. The diameter of these segments are given here, the Young's modulus is given here, and the original length is given here. The question is to determine the displacements of points B, C, and D. If you recall, in another video we said there are 4 major steps, right? The first 3 steps are that in each of the segments we need to determine the axial force, axial stress, and the axial strain, right? Then in step number 4 we use the strain displacement relation to evaluate the displacements. We were able to combine steps 2 through 4, the last 3 steps, and come up with these equations for the displacements at these points, point B, point C, and point D. So on this basis, let's define 2 reduced steps here. Step 1, we still have to go ahead and find the axial forces in each of the segments. Step 2, we use these equations to calculate the displacements. Let's go ahead and start on step 1, where we determine the axial force in each of the 3 segments. Since we covered analyses like this in statics, I will not spend too much time here, but I'll leave all the details here so you can follow through. So the first thing I did is to evaluate the support reaction at point A, which turned out to be 10 kilonewton acting to the left. In this first section here, we are sectioning within AB and considering the left side in order to find the internal force NAB, like shown over here. In the second part here, we are sectioning within the middle section BC and considering the left side one more time to evaluate the internal force NBC, and NBC works out to be minus 15 kilonewton here. And in the final part here, we are sectioning within CD in order to find the internal force NCD. And here we are considering the right side because right side is a lot easier to deal with than the left side. In each of these cases, the axial force is marked as tension, and therefore if you get a positive number, that is a tension. If you get a negative number, that's a compression. Now let's work on step number 2, where we determine the displacements. Our formula for determining the displacement of a single segment is NL over EA. When the rod has multiple segments, we keep adding the displacements of each segment appropriately, like given in these formulas. When we add displacements coming from multiple segments, we also need to have a sign convention. Our sign convention here is tension is positive. By looking at these formulas, you can see it is to our advantage to calculate the deformation of each segment first, which are these quantities, and then go ahead and calculate the displacements of these points. Here are the details of my calculations for the deformation of each segment. First, I listed the forces we calculated in the same table that included values for the Young's modulus and the length. Then I calculated the deformation of each segment separately, starting with the deformation of AB. So this is the formula, UAB equals NAB times LAB over EAB times little aab. NAB is 10 kilonewton from this table. LAB, the length of AB is 1 meter. Young's modulus of AB is 200 gigapascal. So let's convert that into kilonewton per meter squared. So I need to multiply 200 by 10 to the 6 in order to achieve that. Cross-sectional area of segment AB is pi r squared. The diameter of the first segment is 10 millimeter, and therefore radius is 5 millimeters. So let's express that in meters. That will be 0.005 meters, right? Let's square that. And that gives me a value of 0.637 times 10 to the minus 3 meters for UAB. Now you can follow the remaining 2 steps very easily. because the numbers come directly from the table and the diameters that are listed over here, right? And don't forget the signs. So these two displacements are calculated to be compression as opposed to tensions. Here's a summary of the deformations we calculated. Since these numbers are very small, it's convenient for us to express them in millimeters. So this will be 0.637 millimeters, and this will be minus 0.164 millimeters, and this will be minus 0.189 millimeters. Now we can go ahead and use these formulas to calculate the displacements of these points. Here they are. That's it. These are the answers to the questions. You may want to know that as you move to the right from point B, the displacements actually decreases, right? So here we have 0.637 at point B. It's only 0.473 millimeters at point C, and it's even smaller at point D. Now the reason is that these two segments BC and CD, are experiencing compression, and therefore their respective lengths are actually decreasing, right? So this is where using a sign convention is very important in getting the displacements of various points on the rod correctly.